Hello everyone, welcome to the introductory video series of Basic Electrical Engineering Lab. So this introductory video series will comprise of 3 to 4 short videos which will help you understand the prerequisites, or you can say the basics which are required to perform this electrical engineering lab. So let us now see what we will learn, or what we are going to learn in this series. Firstly, we learn to identify different components such as resistor, capacitors, inductors, diodes. Fine. Obviously, without its identification, you won't be able to utilize them onto your experiments. Secondly, we'll get to know how to use a digital multimeter. Thirdly, we'll utilize that multimeter, or you can say your voltmeters or ammeters, for the measurement of current, voltages, and resistor. And lastly, we'll see the experimental verification of different laws. So let's consider our first prerequisite, which is identification of carbon resistors. Okay, now the question arises as to why the identification of a carbon resistor, or you can say knowing its value, is of so much importance. So let us suppose that you want to practically verify a law. Let us assume it be KVL. You want to practically verify Kirchhoff's voltage law. For that, what you are going to do is you are going to consider a given network. Let's say that the given network is somewhat like this. Okay, so this is resistance R1, this is resistance R2, this is resistance R3. This is voltage source. Let us assume resistance R1 is of 100 ohm, R2 is of 510 ohm, R3 is of 10 kilo ohm. So your aim here would be to find out various voltages across different resistors by connecting a voltmeter in parallel with the resistances one by one. But for doing so, what you'll have to do is you'll first have to identify the set of these resistances from a bunch of resistors. Okay, so a bunch of resistors would be given to you. So this is what a typical carbon resistor looks like. So there would be many resistors looking like this, having different color coding. Your first job would be to identify a 100 ohm resistor, a 510 ohm resistor, and a 10 kilo ohm resistor from it. Now, how will you do so? Because the value of resistor is not mentioned here. All you can see here is a set of colored band of resistances. Okay. So for that, let us now proceed as to what we are going to do to solve its, or to know its value. See, the resistance color coding uses colored band register to quickly identify a value of a resistance and its tolerance. As we have seen in last image, there were certain colored bands which would help us to identify its value. Okay. So generally the resistance value, tolerance, and its wattage rating are printed on the body of a resistor in the form of certain letters or numbers. But when the size of resistor gets smaller, or actually what happens is resistance come in different sizes depending upon their wattage. When the wattage of resistance keeps on decreasing, for example, we are using 1 by 4 watt carbon resistor in our experiment. So size of that 1 by 4 watt carbon resistor is little bit tiny. So therefore, the body of the resistance is not big enough to read the printed value. So in that case, what we are going to do is we should identify some other way to know its resistive value, and that would be with the help of color coding rule. And color coding rule is totally based upon this table. Some of the students may identify this table. This table has already been taught to you in your previous classes, so you must have memorized it with the help of a formula which is B.B. Roy of Great Britain, very good white, having gold silver necklace. So this is the list of possible color bands which could be printed on that label, and corresponding to each color we have three values. We have digit, we have multiplier, and we have tolerance. So generally you will be getting a carbon register in your labs having 4 color bands or having 5 color bands. So there is also a carbon register which has 6 color bands, but that 6 color band, the sixth band shows its temperature coefficient, and those are generally not used in laboratory purposes. Those are generally used for application which require much more accuracy. Okay, so keeping this table in mind, let us proceed to a 4-band carbon register. This is what your 4-band carbon register would look like, and you can decode its value with the help of a formula which is in this form. So the form is: first band would correspond to digit, second band would correspond to digit, third band would correspond to a multiplier, and again the last band would correspond to its tolerance. Similarly, if the resistance is of 5 band, the formula will vary slightly. The formula will now be digit, 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 multiplier, and tolerance. So using this statement, or you can say this formula, we will be easily able to identify as to what is the value of that particular resistance which has been handed over to us. Okay, let us now consider a few examples which would help us better understand the concepts of color coding of carbon register. So example number 1, you have been given a register whose color codes are yellow, violet, orange, gold. So we know, as we can already see, that this is a 4-band register. And for a 4-band register, how do we decode it? We decode it with the formula digit, digit, multiplier, and tolerance. So for a reference, the table is given here. So now let us consider the first digit. First digit would be corresponding to yellow. So for yellow, the first digit is 4. Now let us proceed to second band. For second band, the corresponding digit would be 7. And for the third band, we would be using a multiplier. And against the multiplier band, the color is orange. So now we'll be taking up a multiplier corresponding to orange, which is 10 to the power 3. All right. And as far as tolerance is considered, we'll be taking tolerance of gold band. Let us check what is the tolerance of gold band. So tolerance of gold band is plus minus 5%. So the final value of this resistance would be, in a more appropriate form, would be 47 kilo ohm with a tolerance of plus minus 5%. Now let us consider another example. Before telling you the solution of this, I would like to request you to kindly pause a video for a few seconds and try the solution for yourself. Again, this is a 4-band register. For 4-band register, we would require the formula digit, digit, multiplier, and tolerance. So let us consider the first band, which is green. And for green, we'll be requiring a digit. We'll be going to the digit column of the table. And corresponding to green, I can see the digit is 5. Similarly, for red, we'll also be requiring a digit, which would be 2. Then for band number 3, which is the multiplier band in a 4-band register, it would be 10 to the power minus 1. As far as tolerance is considered, it would be tolerance of silver band, so which is plus minus 10%. So in a more appropriate form, I would write it down as 5.2 ohm with a tolerance of plus minus 10%. Example number 3 here is interesting. Here only 3 bands are given to us. First one is white, second one is violet, third one is black, and if no color has been mentioned here, we would take the tolerance band as no color, and it would have a tolerance of plus minus 20%. So whenever you have a 4-band register and you see only 3 colors, then you will assume that the 4th band is of no color, and therefore you would take its tolerance as 20%. So let us take the digit corresponding to white. It would be 9. A digit corresponding to violet, which would be 7, and a multiplier corresponding to black, which would be 10 to the power 0, and a tolerance corresponding to no color, which would be plus minus 20%. All right. I'm repeating myself. Whenever you see only 3 colors, it will be assumed that the 4th color is of unknown band, which would have plus minus 20% tolerance. All right, so in a more representative way, I would write it down as 97 ohm plus minus 20%. All right. So example number 4 here is a bit different from previous 3 examples. Now, how is it different? You can clearly see it has 1, 2, 3, 4, and 5 bands. All right. So, which means this is a 5-band resistor. I've told you earlier also, in your lab work, you will generally see 4-band or 5-band resistances, although there are 6-band resistances also, and the 6-band defines its temperature coefficient, but they are generally used where more accuracy on the value of resistance is required. So for 5-band resistance, we have studied that the formula changes into digit, 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 multiplier, and then tolerance. So let us now consider first band. First band is orange, and for orange I'll be requiring a digit. So let us proceed to the digit column of the table, and we'll find orange here. So corresponding to orange, I can see here it is 3. Again, second band is orange, digit would be 3. Third band here is black, so the digit corresponding to black here is 0. So let us write down 0. Then fourth band comprises of multiplier. So into multiplier corresponding to brown, which is 10 to the power 1. So let me write down 10 to the power 1. And the last band is the tolerance band, which is violet. So let us check what is the tolerance of violet. It is plus minus 0.1%. So I'll write it down as 3.3 kilo ohm plus minus 0.1%. All right. Proceeding further to another example, this is again an example of a 5-band resistor. So I would request you to just pause this video for a few seconds and try it for yourself. Then I'll be telling the solution of it. So again, we'll be requiring 3 digits and a multiplier and a tolerance. Let us check what is the digit corresponding to brown. Digit corresponding to brown is 1. Digit corresponding to green is 5. Digit corresponding to gray is 8. Okay. Multiplier corresponding to silver is 10 to the power minus 2. Okay. And the tolerance corresponding to a red band is plus minus 2%. So therefore, I can write 158 into 10 to the power minus 2 as 1.58 ohms. So my final answer would be this sequence represents a resistor of value 1.58 ohms plus minus 2%. So in the previous slide, we talked about tolerance of a resistor. So we saw whatever the value of the resistor would be, it always had a particular value of tolerance, which may either be 0.1%, 5%, 10%, or even it may extend up to plus minus 20%. But what actually that tolerance means? So let us consider an example. For example, the value of resistor is 1000 plus minus 10%. So let us now calculate what does this plus minus 10% actually mean. So 10% of 1000 would be 100, which means if I add 100 to this 1000 and if I subtract 100 to this 1000, I would be getting a range which would be ranging from 1100 ohms to 900 ohms. So I can say that individual resistors with the same nominal value are allowed to vary in their actual values from 900 till 100, 1100 ohms, and they would still be considered acceptable. So you can simply say the value can vary from 900 to 1100 ohms and it would still be considered acceptable because it has been already given that that particular color coded resistor would have a tolerance of plus minus 10%. And if any fabricated resistance with an actual value outside this range is there, then you will label it as it does not meet the specification provided by the color coding rule. Okay, so there are certain tips that needs to be kept in mind while dealing with color coding of carbon resistor. The first tip is that the colors brown, red, green, blue, and violet are used as tolerance codes only on 5-band resistors, meaning that the 5-band color resistors which always use a color tolerance band. Secondly, the blank, which means the tolerance band corresponding to plus minus 20%, is only used with 4-band code, meaning that you will always come across plus minus 20% in case of a 4-band resistor, which means that you will only see 3 colors denoted on a carbon resistor. Fine. So in the previous slides, we considered all the theoretical aspects of color coding. But when an actual resistor, particularly a 5-band resistor, appears in front of us, what happens is that, and that too with almost similar colors, and almost similar colors on the both of the ends. So we tend to face a little bit of confusion. What actually students tend to face is, let me show you with the help of an example. So this is what an actual 5-band resistor looks like. So the confusion here would be that the reading direction might not always be clear. By reading direction, I mean, let me put it into simple words, that whether I would start its color coding as orange, orange, for information, this is orange, black, black, brown, or I would consider it right to left, which would give me the color code as brown, black, black, orange, and orange. All right. So in that case, the gap between the third and fourth band, or you can say the gap between the 4th and 5th band, generally gives away the direction of the reading. So you can clearly see here that the tolerance band is a little bit far away from rest of the band, which means that this increased distance between 4th and 5th band will always give you the direction of reading. The band which is little bit far away is always the tolerance band. So you can now see that the direction of reading would be here to here, which meaning left to right, which would be orange, orange, black, black, and brown. So corresponding to orange, I have 3. Correspond again with orange, I have 3. Corresponding to black, I have 0. Again, corresponding to black, I have a multiplier which is 10 to the power 0. And for brown, I have a tolerance of plus minus 1%. So the correct value of this carbon resistor would be 330 plus minus 1%. 330 ohm plus minus 1%. Okay. So the conclusion is that sometimes the reading direction might not always be clear to you. So in that case, what would you see? You would check the gap between the last and the second last band. Okay. Wherever the gap is higher, you will consider the last band as tolerance band. And this increased distance between 4th and 5th band would always give you the direction of reading, which means the band which is distant from all the other bands will be your tolerance band.